We work with real numbers almost all the time. In digital hardware systems, real numbers are represented as either floating point or fixed point. In this video, I'll discuss fixed point number representation and the associated arithmetic. First, let's start with an overview of floating point representation. According to IEEE 754 standard, there are two floating point representations: single precision 32-bit and double precision 64-bit. The single precision format consists of a sign bit, 8 exponent bits, and 23 bits for the mantissa. The double precision format has one sign bit, 11 exponent bits, and 52 bits for mantissa. Let's work through an example to understand how a real number is stored in single precision floating point. Suppose the number is 5.25 in decimal number system. First, let's convert 5.25 in binary representation, which is 101.01. Next, we normalize the binary representation of the number. To do that, we shift the decimal point 2 positions to the left so that only one non-zero digit remains to the left. Now the number is 1.0101 times 2 to the power 2. We can see the number in three parts: a sign bit of 0, an exponent of 2, and the significant or mantissa of 1.0101 as described in IEEE 754. The exponent integer is further processed by adding a bias. The bias for single precision is 2 to the power number of exponent bits minus 1 minus 1. That is 127. So 2 plus 127, we have 129 as biased exponent. The binary representation for this is 10000001. You might ask, what is biasing and why do we add it? Biasing is used to handle the signed values of the exponent so that very large and very small numbers both can be represented. With biasing, the exponent values range between 1 and 254 using 8 bits. Note that 0 and 255 are reserved for special values like infinity and 0. So these are not included in biasing range. So far, we have worked out the exponent part. For the mantissa, we take only the fractional part of the significand, which is 0101, because we always have a 1 to the left of the decimal. This 1 is implicit and we do not include it in mantissa. The final representation of 5.25 in single precision format is a sign bit of 0, exponent 10000001, and mantissa as 0101, followed by rest of the bits as 0. This notation style is called floating point because the radix point, or the point which separates the integral part with the fractional part, can move by changing the exponent value in the representation. It is not fixed, it is floating based on the exponent. There are cases when floating point arithmetic is expensive. However, we may still want to use real numbers, the numbers which have fractional precision and granularity. In such cases, fixed point arithmetic is a suitable choice. Although it can introduce some quantization errors, it is sufficiently accurate for most of the applications. The best way to understand fixed point arithmetic is to quickly review the sign integers. In sign integer representation, the bits from position 0 to 30 represent the integer part, while the bit at 31 represents the sign part. An important thing to note here is that the decimal point is always implicitly below the 0th bit. Even though we do not explicitly represent the decimal point here, but it is below the 0th bit. We digressed a little to discuss signed integers because at high level fixed point numbers can be seen as signed integers with a specified position of the decimal point. In fixed point arithmetic, the programmer can choose to fix the decimal point at a certain location within the whole bit range, where some bits represent the integer part while the others represent the fractional part. For example, if the radix point is moved between the 14th and the 15th bit, the bits to the left of the radix represent 2 to the power 0, 2 to the power 1, and so on. Similarly, the bits on the right represent 2 to the power minus 1, 2 to the power minus 2, and so on. In this case, we have 16 bits to represent the integer part and 15 bits to represent the fractional part and a sign bit. The total word length is 32 bit. Let's look at the structure of the fixed point number representation and then work through an example. Hopefully, this will give a clear idea of the fixed point numbers. In fixed point representation, every number has a fixed word length of W bits that consist of a sign bit, WI integer bits, and WF fractional bits. We denote this fixed point representation in theory by QWI.WF. For example, Q10.7 means 10 bits to represent the integer part, 7 bits for fractional precision, and there is one sign bit. Total of 18 bits. Now let's work through an example and find the fixed point representation of the same number we represented earlier in IEEE 754 single precision floating point. Here we represent 5.25 in Q10.7 fixed point. We have 10 integer bits and 7 fractional bits. First, we take the binary representation of 5.25, that is 101.01. Next, we scale this value by 2 to the power 7. This is also equivalent to left shift of 7. Now the number is 101, 01, 00, 000. The 7 least significant bits are the fractional parts, and the remaining bits padded with left zeros are the integer part. The most significant bit of 0 represents a positive sign. This is the binary representation of 5.25 in Q10.7 fixed point arithmetic. As seen, the radix point is fixed here in this notation. When representing a real number with higher granularity compared to what the fractional bits in fixed point arithmetic can accommodate, some precision is lost. For example, if we try to represent 5.0078 in Q10.7 fixed point format, the least significant bits need to be truncated. Before discarding these unused bits, it is preferable to perform a rounding operation first. This improves the accuracy of the results and prevents the introduction of bias during conversion. Let's work out the representation of 5.0078 in Q10.7. When written in binary, 5.0078 is approximately 101 dot some zeros and ones. This binary representation requires many bits in fractional part. However, in Q10.7 format, we have only 7 bits. Therefore, the number needs to be multiplied by 2 to the power 7 and then rounded. If we multiply 5.0078 by 2 to the power 7, in decimal, we'll get somewhere around 640.99. And when we add 0.5 to it, it will be 641.49. After truncation, the number is 101,000,0001. And here is the binary representation in Q10.7 after truncation. As a common method of rounding, a binary 1 is added to the most significant bit in the bit range that is to be discarded, and then the truncation is performed. By following this process, we can ensure a more accurate representation of the original number within the constraints of Q10.7 fixed point. After working through these examples, we see that fixed point arithmetic uses integers just with a different interpretation. Fixed point arithmetic has several advantages and disadvantages compared to floating point arithmetic. First, the advantages. Flexibility. Fixed point arithmetic provides flexibility in precision, range, and word length. Users can tailor these parameters to suit their specific program requirements, allocating bits for integer and fractional parts as needed. For performance, some operations are faster in fixed point arithmetic, especially on small data sizes. This efficiency can be beneficial in certain applications where speed is crucial. Another aspect is ease of use. Casting integers to fixed point and vice versa is straightforward. Additionally, determining the integer and the fractional part of a fixed point number is simpler compared to the floating point number. The logic circuits required for fixed point hardware implementation are generally less complex compared to floating point. This results into reduced design costs. Some of the disadvantages. Fixed point arithmetic may offer lower precision compared to floating point. Users often have to compromise on precision to maintain a manageable word length or overall design cost. The range of values that can be represented in fixed point arithmetic is typically smaller than the floating point arithmetic. Floating point numbers use scientific notation, allowing for a larger dynamic range compared to fixed point. On performance perspective, certain operations such as division and multiplication on large data sizes can be slower in fixed point compared to floating point. Another disadvantage fixed point arithmetic has over floating point is the lack of native support. Fixed point arithmetic is less commonly used and lacks a built-in support in most programming languages. Programmers often need to develop their own libraries for fixed point arithmetic, unlike floating point. Despite these drawbacks, fixed point arithmetic remains a valuable tool in various applications where performance and hardware simplicity are prioritized over the advantages offered by floating point. To leverage the advantages of fixed point arithmetic, it is crucial for the users to determine the optimal word length for their application. This involves understanding the range and the precision requirements which dictate the number of integer and fractional bits needed. Let's see the steps to find the optimal word length. The first thing is to determine the maximum value m that needs to be represented in fixed point. Then we find x such that 2 to the power x is greater than or equal to m, but 2 to the power x minus 1 is less than or equal to m. So the value of x which satisfies this condition is the number of integer bits required for the fixed point. The value of x is wi, which is the required number of integer bits. Then we determine the required granularity of the application. Using the precision or the granularity requirement of the application, we find the value of y such that 1 over 2 to the power y is less than or equal to g, while 1 over 2 to the power y minus 1 is greater or equal to g. This value of y is the required number of fractional bit, that is wf. Using this method, we can find the number of integer bits required as well as the fractional bit required for a certain application. And the word length is number of integer bits plus number of fractional bits and a sign bit. Let's work out an example to compute the word length in fixed point. Suppose the application has the integer values from range minus 1000 to plus 1000 with the granularity of 0.01. Using the condition which we described earlier, where 2 to the power x is greater than or equal to 1000, while 2 to the power x minus 1 is less than or equal to 1000, we find out that the number of required integer bits wi is 10. Similarly, using the constraint for fractional bits, we find out the wf or number of required fractional bits is 7. The total word length is 1 sign bit plus 10 integer bits and 7 fractional bits. That is 18 bits. For this certain application, a fixed point arithmetic of Qm.n is sufficiently good to get the required range and precision. Next, we round up to the nearest integer in our system. That could be 8, 16, or 32. In this example, we round it to 32. Now let's discuss how to implement fixed point arithmetic in C language. C does not have pre-built libraries for fixed point arithmetic. Here is the script to explain how to implement fixed point in C. First, we define the fixed point variable type. Use typedef to create a custom type for fixed point variables. Here, the custom type is fixed p. Then we specify the number of fractional bits. We can do it using a preprocessor macro. The value WF depends on the granularity required by the application. Now look at the data type conversion. To convert an integer to a fixed point, simply left shift the integer by number of fractional bits. Conversely, to convert a fixed type variable to integer, right shift the variable by same number of fractional bits and typecast it. Here are the two macros to do the conversion. Now let's look at the macros to define conversion functions between double and fixed point. First, the double to fixed. This macro converts a double variable a to a fixed point representation with WF fractional bit. First, it checks if a is negative. If it is negative, it subtracts 0.5 from the scaled value. Otherwise, it adds 0.5. The idea behind this is when we have a negative value, we use the floor after the scaling. And if we have a positive value, we use the ceiling after scaling. And then we cast these value to fixed p type. Fixed to double. This macro converts a fixed point variable a to double considering WF fractional bits. In this case, it divides variable a with 2 to the power WF, which is equivalent to left shift by WF, and typecasting it to double. To perform addition and subtraction on two fixed point variable with the same granularity and handle the overflow, we can define macros. In addition and subtraction, if the result is outside the maximum or minimum integer range that can be represented in QWI.WF format, then it is limited to maximum and minimum limits. These limits can be defined in macros as hash define int underscore max value 2 to the power WI minus 1 and hash define int underscore min value minus 2 to the power WI. Here is the macro syntax to do the addition of two fixed point numbers. It's hash define fixed underscore add, which takes two arguments a and b. If summation of a and b is greater than int underscore max value, then it is limited to int underscore max value. However, if a plus b is less than int underscore min value, then it is limited to int underscore min value. Otherwise, it's a plus b. Subtraction macro is similar to addition. It's hash define fixed underscore sub a comma b. If difference of a and b is greater than int underscore max value, it is limited to max value. However, if the difference is less than int underscore min value, it is limited to the minimum value. Otherwise, we set it as a minus b. These macros provide convenient routines to perform addition and subtraction on fixed point numbers, while ensuring that the overflow is properly handled. Now the macro which performs the multiplication of two fixed point numbers a and b and handles overflow. It takes advantage of C's statement expression extension to encapsulate the entire operation in a single macro. First, it declares a fixed point variable r, then performs the multiplication of a and b and stores the result in a temporary 64-bit integer temp. Then a rounding factor 2 to the power wf is added to the resultant temp, and then a right shift by wf to adjust the position of the fractional part. Similar to addition and subtraction, it checks if the result exceeds the max and the min value. If so, it limits the result to int underscore max value or int underscore min value, and then it assigns the temp to r and returns r. This macro provides a compact and efficient way to perform fixed point multiplication with overflow handling. Let's understand the macro for multiplication using a graphical method. If we multiply two fixed point values, each with 11 bits above decimal, 10 integer bits and 1 sign bit, and 7 bits below the decimal to represent the fractional part, then we end up with an intermediate result during multiplication, which has 20 bits above decimal and a sign bit, and 14 bits below decimal. Now, out of this big range of bits, what do we actually care about? We want the output of this multiplication to be in format Q10.7. So we care about the bits that immediately surround the decimal bit. Everything after the 7 bits is an underflow. Similarly, anything above decimal after 10 bits and a sign bit is an overflow. Now let's see a macro that performs a division on two fixed point numbers a and b. Here is the breakdown of the macro. First, it declares a fixed point variable r. Then it checks if the divisor b is not equal to 0. This is to avoid division by 0 error. If b is not 0, then it performs the division of a by b. It left shift a by wf bits and then the long division is performed. If b is 0, indicating it is a division by 0, and exits the program with an error code. This result r is returned. Besides these macro, we can implement other operations in fixed point arithmetic, such as square root, absolute value, and rounding. This would allow us to develop a complete library for fixed point arithmetic and leverage its benefits in design. This concludes our overview of fixed point numbers and associated arithmetic in C. Thanks for watching.